Okay, so with Neil, we'll be discussing NIRPS. So I'm here on the behalf of a very large team. So all you need to know about NIRPS is, well, the Near-Infrared Planet Searcher. It's, you guessed, it's a PRV spectrograph, no big surprise. But just to go back to the history of the project, so with people in France, the Spirou team, basically, we responded to a call for proposal for new instrument on the ISO NTT in La Silla. So René Doyon, Jean-François Donati, and others, we basically said we will want a copy, an exact copy of Spirou at the ISO NTT. So we went to the Canadian Fund for Innovation. They funded the project, and then the ISO selected another instrument for the NTT. So we ended up in panic mode with money and nowhere to go, which is not, usually it's the other way around. We have somewhere to go and no money, but we were in the reverse case. And basically ISO said, well, we have a suggestion for you. There's another team, Portuguese team, that had a design that was very close to what is NIRPS today, because NIRPS is not a copy of Spirou. And they said, well, you're invited to basically to go to the 3.6 meter, which is just next door. If you've been to La Silla, it's you can walk from one to the other, and same size of telescope. You would not have Spirou, you would have an AO-fed instrument, and in parallel use to HARPS, which was different. So we had to go back to the Canadian Fund for Innovation, said, well, we told you that we would correct activity with spectropolarimetry, as we do in Spirou. But, well, no, we'll use an optical spectrograph instead. And they didn't know much about PRV. And they said, yeah, well, we want you to find planets and have a good way of basically assessing stellar activity. Just, yeah, go ahead. So we basically did not lose the money that were ultimately paid for NIRPS. And yeah, and we moved away from the copy of Spirou design to what is NIRPS now. So NIRPS became the infrared arm to HARPS. I guess you're all familiar with HARPS, so it's an optical spectrograph. It's kind of the grandfather or grandmother of PRV spectrograph that are at the meter per second. It has no, so NIRPS has no polarimetry, so we dropped that. It just does not fit on the science array at the resolution we want. There's no K-band, but we left space for that because it would be interesting to go to K-band, so I'll mention that at the end. The instrument, as I said, is AO-fed, and it's just next door to where we imagined it initially. So in a nutshell, so it's an instrument that goes from basically Y-band to H-band. It goes a little bit past 1.8 microns, which is not interesting for science, but it's interesting because you measure tellurics, and you want to measure tellurics to correct them where they're shallower. It's AO-fed, as I said, but not single mode. There's a big subtlety here, and I'll talk a lot about modal noise because that's one of the problems in NIRPS. When you feed with an AO system, you either use your AO to inject a single mode in a fiber, eye locator style or other instruments like that, or you say, no, I just use as a light concentrator to have a smaller fiber. And that's what we do with NIRPS. We aim for 1 meter per second stability, at least within a night, and being able to calibrate over the life of the instrument at the meter per second. So you don't want, so being stable at 1 meter per second over years is unrealistic. I think no instrument does that. Be careful. Stable, I mean, if you did not calibrate, of course you can calibrate back to the meter per second. So calibrate to meter per second within a night. So stable within a night and calibrate over the lifetime. So, well, we have lots of heritage from Spirou, as I said. Also, Spirou has its first light earlier in 2018, so about 5 years before NIRPS. So there's a lot of heritage by ARPS and Espresso, of course. It has 2 fibers, and I'll come back to the 2 fibers. There's a high efficiency mode. It's a 0.9 arc-second fiber that should have about 80,000. I say should, and you'll see why. Should have 80,000, and there's a high accuracy mode, which is smaller. So it was meant to be used for bright targets, and it should have had 100,000 resolution. And well, as I said, we have a continuous coverage from the optical, from basically nearly the UV to H-band. with a gap, obviously, between 0.7 and 1 micron. So that's where we guide. You need photons somewhere to guide the AO. And not to be overly excited, but we had, at least the last call for proposals, we had the highest pressure of any instrument at ESO, the joint HARPS NIRPS. And yes, not just on 4 meters, including VLT instruments. So it has a really high pressure in terms of proposal. The who's who, so the instruments built, it's a consortium of 6 countries. So in Canada, but it's basically UDM, centered at UDM. Université Laval in Quebec City, they did the optics. I'm the project scientist. René Doyon, here locally, that I guess most of you know. He's the co-PI with François Bouchy in Geneva. And Neil Cook, sitting next to me, and he'll talk about data reduction. He's in charge of the data reduction on the Canadian side. There are 2 data reductions. He'll mention that. Of course, we have lots of students involved. People in Switzerland, they did the front end of the instrument. So basically, at the end of the fiber, it's Canadian part, and above so when we inject in the fiber, it's the Swiss part. There are people in France involved. Lucille Mignon, she's doing the very hard work of scheduling, and mention that later. People in Portugal, Spain, and Brazil also involved. Let's say, very, very crude summary of how the instrument is designed. So you have light coming from the telescope. There's a dichroic that sends part of the light to HARPS. We cut at about 700 nanometer. We have a dichroic. And then light goes into a wavefront sensor, as I said, between 700 and about a micron. And that's feeding the AO. It means that you cannot go for extremely red objects but that's beyond PRV. But if you say, oh, I want to do, let's say, a late L dwarf, the brightest late L dwarfs, it wouldn't be crazy, but that becomes challenging because of the AO, that you need some flux in this band, provisions for K band, and then we inject basically in either fiber. Here's the real metal plate with some artistic license on the optical path. It gets more confusing than the diagram. Inside the can, inside the spectrograph itself, we have a very compact design, and I'll show you later the size of the NIRPS optical bench compared to Spirou. Everything scales down with the fiber size. So if you have a smaller fiber, to go at a given resolution, you need a smaller grating. Therefore, you need a smaller parabola and smaller optics and a smaller everything. You end up with a smaller cryostat and a cheaper instrument. So having AO allowed us to have an instrument that's about 40-something centimeters, so 16 inches, I guess, long, something like that. In length, it's a very, very compact design, at least a factor 2 smaller than Spirou, because of the smaller fiber, 0.4 and 0.9 arcsecond instead of 1.2. So fiber size drives everything all the way to budget, which seems weird, but when you think of it, if you want a resolution and you want a fiber size, you've basically constrained everything in the spectrograph. And here's a CAD showing Spirou at 1.2 arcsecond fiber and NIRPS side by side, basically, just to highlight the difference in size of. It's impressive when you see the instrument in person. That's side view of the instrument. And Francesco Pepe mentioned that the most stable, and they did simulation and so on, instruments have a vertical, basically, dispersing train. So we use that from the wisdom of Francesco that you'll hear next month. So the dispersing element are here. And we have a big stack of dispersing prism, because so for those of you that worked at infrared wavelengths, there's little dispersion of glasses in general in the infrared. So you need to stack many prisms, more than you would for an optical spectrograph. So that's the real life beast. And one of the very first, I think, very important element in NIRPS is, it's cryogenic, of course. You would not observe infrared wavelength without a cryogenic instrument. And we're exceedingly stable in terms of thermal stability. So the goal, that was a big topic of discussion in the design, was to have a millikelvin stability over a day. We're at about 1/10 of that. So we're talking hundreds of microkelvin differences. It's even challenging to the measurement system. And once you put that in real life and you have a Fabry-Perot sequence, you're seeing basically an RMS at the below 10 centimeters per second in the lab. I'm not saying we do that on Sky, okay? Be careful. But the stability of the instrument over here, it was hours. We were drifting at about 1 atom per hour on the focal plane, which I think is crazy. I always say that, it's crazy. The instrument, the focal plane, the motion of your focal plane in the Fabry-Perot test sequence is about 1 atom per hour. And ultimately, the calibration goes back to anchoring a Fabry-Perot to a uranium neon. I will not mention the laser comp because it's messy. But we are able to calibrate to below 0.5 meter per second with that Fabry-Perot. But the good news is that, okay, and the one thing that this implied is that there's everything in the instrument to use the Fabry-Perot simultaneous with observations. And at some point, we realized that it was pointless because the instrument is so stable that you can trust that within a night, it will drift so little that it would actually worsen your PRV performance if you use the Fabry-Perot simultaneously. So we just calibrate at the end of the night and it works. So these are pictures in the lab. I had too much fun with a wide-angle lens. Don't think that this is inflated. It's a cylinder. So we had the first light in mid-2022. The instrument, of course, was delayed. You guessed it's COVID. So that delayed by a good year the project. We had first light in 2022. We discovered much to our horror that the grating was problematic. So I'll show you the images we got initially. At least a half of the light was dispersed in a horrible pattern that stretched over the entire width of the array. So we had to buy a new grating. That works very well. There's one mystery linked to it. If anyone knows the answer to that mystery, seriously, you win a wine bottle because we really scratch our heads. We still don't have the answer to it. We started the GTO in April 2023. So by providing NIRPS to ESO, we had a deal where we received 40% of the telescope time. So that's 720 nights over 5 years. And that's a very Canadian perspective, but it's more than all the Canadian time at CFHT over the same period. So it's a crazy amount of time. Of course, it's spread over the entire NIRPS consortium, so people in six countries, but it's a lot of time for PRV work. And not just PRV, we have also transit spectroscopy, eclipses, and so on. Last year operation, so the GTO team, so I said we have 40% of the time for us, but people that receive, that are awarded time at NIRPS, they may, if they want, join basically the time share. And so we manage, it's nearly 100%, not exactly, but nearly 100%. So between 80 and 90% of the time is managed by the GTO team. So the idea is that if you don't join that shared time, well, you have a night at the telescope, you go there, that's it. But for PRV work, that's terrible. I mean, how do you monitor a planet on 5-day orbit and properly sample it if you just go for a little run at the telescope? That doesn't work. So unless it's something completely different, let's say chemistry of stars and so on, people will want to join that timeshare. And it's managed by Lucille Mignon in Grenoble. She does a fantastic work scheduling the targets and trying to basically optimize the entire queue of the telescope. It's great for PRV. It's great for transit and eclipses. So of course, if you were awarded time for transits, unless it's a super short orbit, you most likely will have windows spread over many months. So no, you're not going to Chile every time the planet passes in front of the star. You just join that timeshare. It's a huge commitment for the team. And I put it in bold and italics. Managing an observatory is big. It's done by Lucille. She does research. It's done also with, we check the data. It's done by students. And yeah, I don't know if we really understood what we committed to when we did that. So we have a whole group of babysitters in Montreal that basically the students that check the data. So Neil could, if you have questions, he could mention all the quality checks we have. And of course, problems are correlated with weekends and holidays. They never happen on Wednesdays, the problems. They always happen on Saturday morning. So that, I don't know why, but that's just life. So yeah, so we have people that's out of date, but students that are every day check the data, and every Monday we have a whole meeting just to double check that everybody, including PIs, have good data. So how does it work? And I'll get to science performances. One really good news is that the AO works for its intended purpose. So we basically, if you look at the relative throughput, I think that's all the Proxima observations. I'll talk more about Proxima, don't worry. Where you have the relative throughput, basically the flux we get on this on the detector as a function of seeing from the telemetry of the AO. And the seeing has been bad. And we had El Niño year early in the life of NIRPS. And the flux from below 1 arc second, which is expected normally, to all the way to 2 arc seconds, you have about a 20% loss in flux. And you have the dash curve here that is the encircle energy of a MOFAT profile for that seeing. And you see that past 2 arc seconds, just the AO just quits and it just doesn't work and it just goes to sleep. But all the way to 2 arc seconds, we basically nearly keep the performances of the injection throughput, which is really good news. So it does the job. We're done documenting, and so all the rubber stamps have been passed at ISO, and you know, if you're familiar with ISO bureaucracy, that's a big achievement. We have a first light paper that's out. Yeah, I have links, so I'll share the slides. I guess we could send it with the emails. There are links to the ADS entries. And it's not just good, and we're really happy with performances. So we're below the meter per second. So I'm sorry if other instruments are below the meter per second in the infrared, you can chime in. But I had to say that we're the only, but yeah, we could argue. Okay, as I said, focal plane drift of about an atom per hour. We're applying lots of lessons, especially in the DRS that Neil will mention. And here's a time series, and I'll point to the paper that Alejandro Suarez worked. That's Proxima system. So there's the 5 and 11 days and the rotation, but there's no GP. Okay, so just the rotation and the 2 planets, and you really see nicely the match. That's 1 meter per second, and the RMS is about 75 centimeter per second, the nightly bins. And I'll come back to the photon noise later. So the GTO is split. So we have, as I said, we received 40% of the telescope, and we are split in 3 work packages plus a miscellaneous that I won't get into. So there's a blind search. We basically go for stars that have no known planets a priori. So we have a work package. That's the one I'm leading. It's the below 0.15 solar mass. So it's really the bottom of the main sequence. Yeah, so that's where you really gain the most having an infrared coverage. We have a work package that's as the perspective basically of finding planets that we could image with the ELT, that could be targets for direct imaging in the semi-near future. And we also want a package that has the PACAMARA, the acronym. It's around young stars, so trying to fill in basically the gaps in terms of age of RV planets. There's work package 2. Is the PRV follow-up of transiting exoplanets, so test follow-ups, not only test, but mostly test follow-ups. And transit spectroscopy and eclipse. So that's the work package that had the most papers out to date, just because not just one observation, but you have a handful of observations, you can already write a paper, maybe. And that's a pretty successful one. And that's where we really benefit having access, managing 80% of the telescope time. So Spirou, for example, we only observe in bright time. Well, that's bad. That's 40% of the time, maybe more or less. And well, more than half the transits, you miss them. And with NIRPS, we're nearly, not all, but nearly all transits, we can get them. Data reduction. Neil.
Okay. So yeah, as Étienne's mentioned, there are 2 pipelines for NIRPS. There's the ESO pipeline, which is run at the telescope, and I think in Geneva at the moment. So it's based on the Espresso pipeline. So anyone familiar with that, it's very similar to that. And then we have the EPRV pipeline here in Montreal, which is also used by Spirou, and we're developing it on a few other instruments as well. So yeah, having 2 pipelines has been really great for identifying differences. So if you were at EPRV 6, I talked about that quite extensively and showed you the gory details of how they differ and how they are the same sometimes. And when they are different, which is correct, you have to figure out, right? our staple thing is basically any result has to survive in both pipelines, or you have to know why it's in one and not in the other. And yeah, so are we doing things the same? Are we doing things differently? There's definitely differences in opinion on which algorithm is better, and different in philosophies on your workflows. So we don't always agree, and sometimes we just have to agree to disagree. But you really do have to understand, if there's a difference in flux, or where is that coming from? But yeah, this is not all doom and gloom. They can agree, and they do agree in lots of results. So here is one that is from Avidan. So this is a paper in prep on TOI 406. And the results agree very well within errors between the two pipelines. You'd be hard pressed to tell the difference if you didn't see these side by side. So yeah, in most cases, we make sure that all of the PIs, at least on the GTO, are checking both pipelines, and that their results, are consistent between pipelines. Yeah, so just a little 101 on Apero. So it's written in Python here in Montreal, and it's open source and it's on GitHub. So in theory, anyone can use it. It takes telescope data and produces the standard 1D and 2D extracted spectra. It does the telluric correction. It provides on-the-fly CCFs, and it has the LBL code, which I'll mention after this. It's sort of integrated into it. And it is written to be able to support new instruments fairly easily. So again, we started on Spiru, and within a few weeks we had it working on NIRPS, and obviously with continuous development thereafter. And we've recently added SPIP, and it didn't take much work. It was a couple of weeks just getting it working with SPIP. And an Apero will be used for iLocator in the future. It's also relatively fast, which is one of its advantages over the Espresso pipeline. You can really multi-process in parallel. For example, with Spiru, where we have about 100,000 observations, so all 5 years of data, probably more like 6 now, we can reduce all that data in about 3 weeks. So it's really a nice turnaround with Python being, you can make a change very quickly and then implement it quickly and then reduce your data. And the details for this are in our paper from 2022. And for LBL, this is just a very quick 101. I think Étienne, if you want to invite him back, could probably talk about LBL for a whole hour at least. So yeah, it's basically an alternative to the classic CCF method. It's very similar to template matching with some differences. It's all explained in the 2022 paper by Étienne. But basically, in a nutshell, it basically takes your whole RV, your whole spectrum, and cuts it into chunks or lines. I prefer chunks to lines. And you work out the RV on each of those lines. And once you have the RV on each of those lines or chunks, you can then combine that and reject bad chunks. Yeah, and we also have it working on both the pipelines for NIRPS, so you can really compare the results from both with the same algorithms for doing the RV. And it normally starts with the telluric corrector files. And as well as this, it also works on many other instruments, and we're happy to add more instruments. There is a generic mode as well, so you can just, if you get your data into a certain format, it will work. And we want also to support the EPRV standard in the future. But yeah, for now it works on Spiru, NIRPS, Harps North, Espresso, Marinex, Comines, Sophie, and Coralie. Yeah, and it seems to be giving good results on all of those instruments. Yeah, so that's it for the sort of overview of the data reduction very quickly.
Okay, so one thing that when people give talks on instruments, and I saw it a little bit on at EPRV 6, is that there's a tendency to say, oh, it's all fantastic. You show the representative results and say this is yeah, you take you cherry pick the best and say it's representative. So I'll show you ugly things that happen with NIRPS. So this image is a holocatted observation before, so with the back grating that we had when basically we built the instrument. And there are, you can see like these big ribbons there. And if you, here's a zoom in on a specific region of the array, you see this pattern of structures. That's not real. That this is diffraction and basically errors in the groove making that sent a diffraction pattern. If you set a laser to the inside, which is basically what you get when you have these very bright lines, we had big arcs that span the entire width of the array, half the light not going where it should, and making structures that would contaminate other spectroscopic features. So we thought of going to science with that, but that would have been a real bummer and well, stopping us from getting the PRV performance just because you have contamination between others and also wavelength solution. So we went with IOF for another grating that's here. Basically, you see all these arcs disappearing. There's scattered light. That's just life in an instrument. You always get scattered light and you have halos around bright lines, but that's okay. And you see it's very, very clean between bright lines. So the IOF change, the grating change was a very good thing. We adjusted the blaze and so on. We had a resolution that's slightly smaller than we expected because of a blaze adjustment we had to do. The blaze was not exactly where we wanted it to be. That's life. So, and there's a mystery. We still do not have the answer to that one. If we looked at with the old grating at the resolution was below what we expected from probably from the structures that were basically it was probably an inhomogeneity in the line spacing of the grating. So that's probably why we had about 80,000. We changed the grating. We had about 90,000, so the modest improvement. But there's a gradient, and it's still in NIRPS. There's a gradient if you look in pixel space, basically in the resolution. So we have about 90,000 where the blaze peaks. So that's where you get most of the flux. But where you're really on the side of the blaze, you get about 70,000, even a little bit below. And we can say, well, your detector is tilted. No, it doesn't work because it's only in one spatial dimension. So that does not make sense. And optical engineers scratched their heads and we never found a good explanation as to why. We did the math of the RV content impact. So always, of course, if with a PRV instrument, if you worsen the resolution, you lose fast in radial velocity accuracy at a given signal to noise. So we did the impact. The good news is that where you get this very lower resolution, you have very little flux. So it's a domain that counts very little in the end. So that's not a big deal, but we do not understand optically why. And we thought, okay, do we want to spend 3 months investigating or just go and observe? We just said we just go and observe, basically. Modal noise. So as I said, NIRPS we're injecting in the fiber. So the AO is used as a light concentrator, not as an injection of a monomode fiber. So we have 2 fibers, and if you do the math of how many lambda over D you have on each fiber, in H-band is the band that matters most for RV content. You have around 16 modes in in HA, high accuracy, and about 80 modes in HE, okay? And early on, we identified this as a risk. We knew that if we had modal noise, that would be bad because it would set an upper limit. You have a fixed pattern, and I'll show it to you, a fixed pattern. And if you go to 300 of signal to noise, but you have a modal noise at 5%, you have 20 of signal to noise in real life. So that's something we knew. Nicolas Blais in Geneva did a lot of work, and we have 3 things that we do to correct that. We stretch fibers. Literally, there's a stretching, mechanical stretching to scramble modes. We scramble also with the AO, so you can move the PSF on the fiber itself, and you can also calibrate in part.
Chad is asking the physical size of the fibers.
In microns? Oh, it's I have actually the dimensions in a little movie. It's 90 microns and 130 something, but it's an F4 beam. Yeah. No, is it F4 or F8? Oh, I could double check that. Yeah.
Okay. But you said 90, not 19, right?
It's 90. Oh, it's actually in the little movie that's coming.
Okay.
No, is it? I had the size. Oh, I could find it. I think it's the HE fiber. Okay, it's 132 micron by 32 microns.
Okay, that's pretty big.
That's pretty big. But you enter at F8, which is also important. It's not just the fiber size. It's what's the F number you enter in. Yeah.
Thanks.
And the short, and I'll get to that. The short answer is HA is basically useless. So all you need to remember is HE has 130 by about 30 something micron. Yeah. And enter that F8. So if you want to see modal noise, here's the high efficiency fiber. So we redimension an octagonal fiber into a rectangle. And here's the HA, it's a magnification, but the octagonal fiber that makes the HA mode. And if you wiggle the fiber, you see a pattern that's changing like that. And that pattern, well, it does two things. It moves, it changes the throughput with wavelength. It adds a fixed structure, but it also moves the barycenter of your flux. If you have had a monochromatic line, it can wiggle back and forth the center of that line. So it's bad in two ways. You have a spurious structure that's limiting your signal to noise and a motion of your lines. So once again, so that's just bending basically the fiber. So the idea of the stretching and the scrambling of the AO is, you know, there'll be modal noise. There will be modal noise. But if you cycle through the noise fast, it will just average out. That's the idea. So another way of seeing modal noise, if you take a flat field, that's a flat field in HE. So in HE does the same. It's just easier to see in HE. That's a normal flat of the fiber. And if you take two flats days apart and you subtract them, you see structures like that. And if you extract that, of course, you will see structures in your flat, and they vary, and they are also present in science. If you have a really sharp eyes, you will notice one thing. It's worse on this side and it's better on the other side. Anyone knows why? No? Anyone wants to guess? Shorter wavelengths, more modes, they average out more. Longer wavelength, fewer modes, they average less. That's also why, as the same fiber in the optical, but you wouldn't have the AO. Okay, but let's pretend you could do the same thing at 0.4 micron. You would have a very, very small modal noise because you have far more modes in. It goes as the square of wavelength, but 1 over square of wavelength. That's an example of a flat field, of many flat fields taken in a row with nothing done, and you have a percent level, many percent level structure. So that's a spectral domain. I don't remember. It's probably an H-band because that's where it's worse. And if you subtract the mean of all these flats, you get both basically your photon noise. But if you observe a star, well, you'll have this embedded in your structure. So you say, well, I'm fine. If I have it in the flat field and a star, I'll be fine. I'll just flat field it. No, it's not that easy. They are not identical to the flat field because the flat field is a flat illumination of your fiber. A star is a point source illumination of a fiber. It's somewhat of a worst case scenario. The best case would be, no, they just average out in seconds. And it evolves extremely fast. That would be the best. Another good case would be, no, they are stable over many, many months. And part of it, and I'll show what part of it is stable in many months, and would be fine because you can just calibrate. But no, they vary within the night. So it's neither the average out nor the survives a long time case. So what we do, we stretch, we scramble, and everything. We realize that the the initial modal noise is much larger in HA. The reduction is more modest in HE, but in the end, basically the HE mode outperforms HA easily. We also observe hot stars, and yeah, they are used for tellurics, but they can also be used for calibration of the modal noise. So the flow down of the budget, basically out of the box, you have about 6% of modal noise. If anyone's designing a spectrograph with a similar number of modes, you better have a plan. Okay, you better have a plan if you want more than about 40 of signal to noise. So we stretch, we scramble, we calibrate, and we're between 1 and 3 parts in 1,000 in HE mode, and that's good enough for the meter per second. Okay, if you wanted to go, you can go beyond that. For example, if you go do some transit spectroscopy, if you're stable on a single star, the modal noise doesn't change that much. So you can go even further. but between nights, you cannot get below above, basically a signal to noise of about 300 in practice. So 2HE or not 2HE, that is a question, and we had to decide earlier, because when you start the GTO and you start gathering PRV measurements, you need to pick wisely, because you cannot anchor basically an HE and an HA measurement easily. And we checked on a few stars, Proxima, JJ, well, you recognize the names, the RMS of the time series and the nightly errors. And actually, we saw that the HE gave lower errors, lower RMS all the time, basically. This is Spurious point. So basically, we decided not to observe with HA unless you have a really good reason. The really good reason may be tight binaries. If you have a tight binary, you want to put your fiber on it, well, of course, a smaller fiber is good. You have less sky background. But other than that, if you want to do PRV below about 1.5 meters per second, you need to go with the HE. If you go on faint targets and the AO does not perform very well, you want HE, not for modal noise, but for the geometric size. Now the slinky. So you think you understand all the modal noise. There's a very strange effect that I couldn't find any other name other than slinky. We had caterpillar at some point. We converged on slinky. So you have an HE, that's your HE fiber, and you have a blob due to the modal noise. Do you care? Well, yeah, you care in flux, and I showed in flux, but you also care in wavelength. Because what happens? If you have your blob and it moves elsewhere, or there's another blob appearing, what happens? It basically moves the flux barycenter in your fiber. So if you have a perfect wavelength solution, you have wavelength and pixel, but you're happy it's a straight line, or it's a simple polynomial, and you're just fine. If you have a fixed speckle, it's okay, because it just offsets your wavelength calibration. That's fine. Being wrong, always the same is okay. But then if you have a blob that goes from one side to the other side, you'll have a kink in your wavelength solution. And that's a problem. And do they exist? Of course they exist. So we looked at these are Fabry-Perot lines, okay? So each point, and they are color-coded per order. So we have a little bit of an order, a full order in green and the next one. And it's the Fabry-Perot lines relative to the smooth, basically, model of the Fabry-Perot cavity. And we see back and forth at about the 10 meters per second in the position of the Fabry-Perot lines. And they are really consistent between orders. So it's not something geometric. So some people argue, it may be pixel effects. But don't forget, the green and the red, they are seen on the two sides of the science array. Okay, so they see nothing in common in the optics past the grating. So once you're past the grating, they're literally on the two sides of the array. So it cannot be a detector effect because you will not have the same modulo 1 pixel. It cannot be a Fresnel propagation effects in the optics because you're literally not at the same place on the optics. So it's really, it's really an effect of slinky, contraction dilation of your wavelength solution. And how long does the slinky live? So I said the flux part of the modal noise lives on a relatively short hours timescale. The slinky is very long-lived. So if it evolved between frames, we'd be okay. Hour to night timescale would be worst case scenario. And over many nights, we can calibrate. Or it could be fixed over the life of the instrument, and we don't need to talk about it. So we're in the evolves over many nights case. So we did a plot of the slinky as a function of the Julian date. And you have epochs. The instrument just changes states. At some point, your slinky changes. And actually, we could map these events. So you have one shape of a slinky, then it goes from red to green to blue at discrete epochs. And we can map it. It's actually when we warm the instrument or we fiddle with the injection of the instrument. So we're seeing something in the very close to the injection that changes in diffraction pattern when we disturb the instrument. So we are working on an implementation of that in the Apéro. We had other issues. So I was going to tell you things that went wrong. You'll probably see those because that's common to all instruments. We have a sky model. So we have a sky fiber, but it doesn't work perfectly. and we have a sky model, and then we discover that things went wrong in J-band. And there's a strong emission feature in J-band. Basically, if you have hours after twilight in a time series on sky, you can see some lines are very, very short-lived, about an hour. And that's bad, because if you construct sky frames in the middle of the night and you apply them in the first hour of the night, you have a problem. And it's even worse than that, because these features, they are exactly the same as telluric absorption features. It's actually emission in the same lines. So we had a very hard time at some point converging on telluric absorption, because we had sky emission filling the absorption features from the tellurics. So you try to measure something as an absorption that has an emission feature in it. It was very messy, and it took us a long time, so I'm just sharing the info. If you're really scratching your head about weird telluric behavior in the first hour of the night, double check your code, how you converge on the, basically, double check the arithmetic and how you handle this fluorescence within J-band. Oh, now the BERV 0 point. Okay, that's Spirou data, because it's bigger in Spirou. Okay, so I'll be showing Spirou slide, but the same is seen in NIRPS, and we had issues. So this is worth an explanation. On the left, focus on the left and explain the right after. On the left, you have many stars. They're all color-coded. So it's many stars we observe with Spirou. And I plot the RV time series, but not with time. With, at that moment, the sum of the systemic velocity of the star plus the barycentric motion, okay? So if you have a spectroscopic feature, I don't know, H-alpha emission, that's basically the velocity of your H-alpha emission that you're measuring at that moment on that star, okay? And it's very interesting, because there are wiggles that are correlated between stars. So what does it mean? It means that you have telluric features that overlap with spectroscopic features. These are all M dwarfs. So you have a random iron hydride, I don't know, something in the M dwarfs that overlap with a telluric line, and there are finite resolution effects, for example, that mess your telluric correction and affect your EPRV measurements. And it gets really worse at there's really an S shape or Z shape, depending on how you see it, are between -5 and +5 meter per second. And it's seen in all stars that have that BERV, barycentric RV, 0 point. When you overlap, basically when the water lines in the M dwarfs overlap the water lines in the sky, and it's the same molecule, so you will have an effect, and there's this structure. So it's non-trivial to correct. You can pass a GP, so that's what we did we constructed GPs in BERV space and in time space. So this is nights, basically. So of course, which star passes at BERV = 0 on a given night? Of course, it depends on the star. It depends on the systemic velocity. So they are folded differently if you express things in time or if you express in BERV. But yeah, we were able to improve things. It's not perfect yet with that BERV crossing. So that's after a GP correction. Still not perfect. But we have to be careful. And you'll see in some NIRPS papers when you mentioned this, there's one really nice paper by Lena Park that's coming. And we have big issues on this target with BERV crossings. So you'll see, if you see that mentioned, this concept, and check for that in your data, infrared spectrographs, check for the moment, and it's easy. It's just simple arithmetic of your line of sight velocity. Check if you have these effects. That's an example in Gliese 410 in Spirou, where we did, that's a before-after correction. So you had a nice BERV crossing here that you could mistake for an eccentric planet or whatever. No, it's just the BERV crossing. So early science results, I'm getting to the end. We're about halfway through the GTO. We're already thinking and scratching our heads, what's next in the following 5 years? We're having too much fun to just drop it there. I'll highlight 3 papers, Proxima results, and 2, well, it's not PRV, but too bad. It's transit works. And we have lots of papers that are submitted or in late stages of preparation, but it's not public yet, so I won't give the target names. TOI follow-ups, of course. Nice non-transiting planets in systems that are known with a few transiting planets. We have a very weird, massive planet in a long orbit on an M dwarf that's basically in distant orbit to a Neptune-sized close-in transiting planet. That's the one that have BERV issues that we fixed, but that's submitted or submitted? I'm lost, but yeah, submitted or close to be submitted. So you have the links. That's really our favorite target. So we observed Proxima too many times with NIRPS, and we're basically able to recover Proxima B easily, the 11-day planet. We also, with NIRPS alone, without espresso, we recover Proxima D, the 5-day planet. So you have histograms on the RV basically fit of Proxima D with this, all the data, including espresso, and NIRPS only data. And you recover at the phase and at the amplitude of NIRPS, of espresso. So here you have the results, and these include slinky effects. You have to include slinky effects to get this. So it was basically the slinky algorithms are included here, but not yet fully in Apéro. There's Romain Allard. He observes the object to get the helium signature. So helium, you may be familiar, evaporates from close-in planets, and you have this tail of helium that gets out of the in basically a bit like a cometary tail. And we have a really nice spectroscopic map of basically the helium feature here, and you see there's a wisp going away there, and he could basically make a model of that cometary tail, and there's even a little tail before, that's this material going inside. That's before the planet in its orbit. That's a really nice result on non-PRV result. And just to highlight Valentina Vaulato that published a paper where we observed, she observed a planet and detected iron, so transiting hot Jupiter, but not in NIRPS data, but it was detected in HARPS data. So it nicely highlights complementarity of having the two instruments in parallel. And she could constrain the abundance of H- in the atmosphere of that object, which is hard in general, which basically hides the iron features. So that's not my science. I'm just highlighting there's a paper there if you're interested. Path forward, and we're getting to the hour, I guess. As I mentioned, we are thinking, and that may be part of the negotiation with ESO for an extended GTO, of having a K-band in NIRPS. Why? Why K? The most important part is atmospheric studies. You have access to the CO band head at 2.29 micron. There may be an improvement in PRV because we may, if we go to speak this way, go to a very high resolution, maybe 200,000. So a factor 2 higher than the current fibers. We may use, and we're in discussion with a team in Grenoble that developed a technology, a design that is a VIPA. It's called a VIPA, a virtual phase array, virtually image phase array. It's basically a system where you have a slab of glass and you have back and forth. You have it here as a, so you enter with a very, very slow beam, and you have a back and forth in a slab of glass, and that creates a virtual grating. And it's much easier to make a very high resolution spectrograph with that, because it's just the thickness of the glass. You don't need to carve grooves that are a good fraction of a millimeter in size, which is really hard. So if you want to go to hundreds of thousands in resolution, that's the way. That's way easier than a design with a grating, with the caveat that you have to enter diffraction limited. So we may have a single mode fiber, which gets rid of the modal noise. It comes with, it's complex. And going to K-band, you need fluoride fibers, they're pricey. There's thermal background, though going diffraction limited helps because you have a smaller fiber and so on. So we're scratching our heads for that. We, on purpose, left a port in the NIRPS AO system for that mode. And also 70 centimeters per second is nice, but that's not the photon noise. And we just feel bad about that. And at so we are all sorts of improvements to the DRS that we see to go better, actually get better than that. Have a proper slinky correction everywhere. We have chromaticity also of the cavity. So we assume the Fabry-Perot cavity is achromatic. We need to revisit that. This has an impact. For a few weeks, we thought that we had a 200 and something days planet around Proxima, and was super happy about that one. That was like the dream target for ELT, before we discovered that it was due to the chromaticity of the Fabry-Perot cavity, and it just disappeared. That's life. Improvement of telluric correction. The CO2 varies on a multi-year time scale. CH4, it's not included yet. We have a water and everything else approach. That's not totally accurate. So this may help also on the side of the BEV crossing. And we're also working, 2 students, Advani Doshi and André Silva, have published papers this year on templates. We want to improve templates. And we have ideas of how to build a template without interpolating data. But that's in progress, I won't say more. That's it. Questions? Neil, comments? I'll leave the slides on if someone has questions. Oops.
Thanks very much, Étienne, and Neil for a really interesting talk. Yeah, so if anyone has any questions, otherwise I've got a handful here I can throw at you. I'll try to give people a minute. I guess maybe to start off, because I actually didn't realize the legacy that NIRPS was at one point supposed to be Spiro 2.0. In the transition between the designs, what would you say is you're most excited about in the NIRPS design that wouldn't have existed in the Spiro design, and then vice versa? And this, what are you most missing about the fact that you didn't go with the Spiro design in the end?
Well, okay, so we basically René Doyon would tell you the political story to it, okay? But basically, we said we're going to save on the design and just copy paste Spirou. Spirou, I think, okay, so it's the same code that, as Neil said, it's the same code that reduces both data sets. Spirou does not get to the meter per second or below. And we're pretty sure that the code, one of the two things, let's say, are probably responsible for that. The complex slicing of Spirou basic fiber. So you have kind of it looks like a barn roof, and you arrive on it and just sends basically parts of the pupil, and it's pretty complex. It works, but you basically reshape your pupil into 4 and so on. And we think that that's the cause of some of instabilities we see in Spirou, is that injection model. But we've never been able to prove it. The second thing is that Spirou has a factor 2.2 larger pixel. NIRPS is at about 1 kilometer per second. Spirou is 2.2 kilometer per second. So any problem, anything, will scale with that. So there's a 2.2 penalty anywhere in Spirou in terms of stability. So that's the thing. Let's say we had, I think that was wise in the design. So basically, we adopted mostly the design that the Portuguese and the Swiss had. The Donati team in Toulouse, they said, okay, we're not joining if it's not a spectropolarimeter, so they dropped. The Grenoble team that was with us, with the Toulouse team, said, oh, we're still in, and they're still in. So yeah, so we mostly adopted the Swiss plus Portuguese design and joined them, but had the money for the Spirou that we put there. So it was very messy. You can imagine like the head scratching we had with the deans. It's like there's a whole talk by René that he could give on the politics of all of it. So there's nothing for Spirou that we really miss.
Okay.
K-band. Seriously.
Okay.
CO band head. Yeah. For atmospheric studies, winds in transits, basically. Yeah, that would be nice. So that's why we're trying to push for a K-band and discussing with the team in Grenoble that have the VIPA design and know all about it.
Yeah, just to highlight that Subert's got a note in the chat to watch out for modal noise in single mode fibers, since these fibers support 2 polarization modes, and put a link there.
So we thought it was a silver bullet. It's like laser comms, okay? Laser comms. okay. I didn't mention we have a laser comm, and it has a lot of personality, and we're still not yet in full in the standard operation. Yeah, but it seems like a silver bullet until you start playing with it. So I get maybe it's the same with single mode fibers. You think they're perfect until you use them.
And what would you say is the most interesting science case that you would open up when you're moving from 70 centimeters per second to 30 to 40 centimeters per second when you're thinking about targeting M dwarfs in particular?
Well, I guess Proxima, because we can have a lot of time, because if yeah, so it's just, yeah, M dwarf, very bright M dwarfs for the ELT. I think that would be interesting. Also, we're working on activity indicators. That we have some exciting results. I won't say more because it's just work in progress with students, but in improving activity indicators in the infrared. So it may not just be that; it may be targets also that are 3 meters per second that you push to 1.5.
Okay, yeah.
So it's not necessarily just, okay, I was just saying, okay, 70 is nice, but we have better than that in principle. We're not far, though. We're not far from the photon limit of the holocathodes. If you do the math, 40 to 50 centimeters per second. So we're not that far, but with the laser comm, we could easily beat it if the laser comm behaves.
I mean, that was one of my questions for you, is you had hinted that the laser frequency comb is a bit messy. Do you have
not stable? It's not stable. I don't know the details. It's François Bouchy that does the work, mostly the interaction. I think it's just not stable in its. It doesn't like being turned on for very long periods. I don't know the details, so you should ask François. I don't want to misquote him.
Fair. And then I don't know. Does anyone else want to jump in? So I've got 1 or 2 more I can ping your way, Étienne. Okay, I will. So you mentioned about having both sky emission and absorption basically overlapping. So how do you actually solve that issue then?
It's not obvious, because
no,
it's not easy. How we do it now, we just fit the dry. We call the dry is basically everything other than water and we actually do not put weight, which we basically excluding the fit that domain. That's a caveman approach. You just hit that bit and just say it's not there. But you apply telluric correction there, but you've constrained it elsewhere. But if we go with CO2 and CH4, we need to see how we implement that. So there's some head scratching on how we'll do things if we want to go with splitting down the dry components of the atmosphere. It's not obvious, but for now in Apéro, we just have a rejection domain. So you correct, then we correct emission after that. But you know that you corrected. So basically, if you know nothing about the object, you just can't solve it. And if you just had that domain and knew nothing about the object, you just can't solve it. We could use also templates. We have templates of the objects themselves. So it's work in progress, but for now we just null it. Chad with the raised hand.
Yeah, Chad's got his hand up.
You may have mentioned this, and if you did, I apologize. I got distracted partway through. But on the laser comb, so you made some comments at the beginning about the laser comb, not being all that one would hope for, and problems with it. I'm wondering, is the issue just the reliability of the laser comb being available, or are some of these other modal properties that you're probing also problematic with the laser comb, even if it did turn on every time you wanted it to turn on and worked?
Okay, the short answer is I don't know yet. We were so busy with everything else in the DRS and the data that we said we need a few weeks to months of laser comm, let's say, embedded in the calibration sequences, and let's just pretend that we're going to correct to calibrate a wavelength with it and analyze it, and we're not even there yet. But it's largely a matter of us not having time yet.
Okay. I'm very familiar with that situation.
It kind of bites its tail. So you don't know yet if it's good enough. Therefore, you don't dedicate time, and But that's
sure.
Yeah.
But it'll be interesting to see what happens when you do get to it, because I think they have a lot of potential and also a lot of issues.
Yeah. Is the slinky the same? I really hope it's the same in the laser comm.
It better be, and I think that the laser comm will solve your problem there, but I might be wrong.
But you would, okay, the thing is that the whole point of the holocathode is to tell you how your Fabry-Perot cavity changed. And so yeah, so if you could use a laser comb instead of the holocathode, that would beat easily the 40, 50 centimeter per second we have as a limit. Though, what do you do if you have 2 months of a laser comb and then you say, oh no, it broke, and so we're sending someone with a wrench, and then you have 3 weeks in the middle that you need to calibrate in another way? That's very messy. That's very messy in terms of data reduction.
Yeah, we've had to deal with a scenario like that on HPF before. And it is messy, and the longer that outage goes on, the more messy it gets. Yeah.
You don't want many if then else in your wavelength solution.
You don't, and it also depends on how reliable your etalon is and how old it is, and how much is it drifting, and what assumptions can you make over the outage. And that's the game that we've been able to get away with. But yeah, there are limits to that.
Yeah, no. So yeah, no. So I don't know all the details of the laser comb. That's the short story.
Okay, well, it'll be interesting to hear once you start digging into that.
Yeah, but honestly, it's a suggestion for Heather and others. We should have a laser comb conf at some point.
Yeah, I'll definitely make note of it for the future.
No, they sound like silver bullets, and then you talk to people.
And I'm sure we will hear about some of that when Francesco talks to us about wavelength calibration next month. I see that we're a little bit past the hour now, so I would encourage, if there's further questions, for you to reach out to Étienne and Neil directly, and just remind everyone that he's gracefully posted his slides in Google Docs here, and linked to them in the chat, so you can check them out there as well. And they have lots of nice links to further resources, so do use that. So, all right. Well, if there are no pressing concerns at the moment, then I guess we will thank Étienne and Neil again for their really interesting talk on NIRPS. And we will see you all next month, hopefully. All right. Thanks very much, everyone.
Bye-bye.
Bye. See you.